society is forcing success down our throat, comparative success down our throat. So we all want to be followed. We all want to lead, I should say, and we're willing to do anything. Young ladies and young men, anything to be influential.
Yeah.
The universal stems from the specific. Where's your soul? Where's your heart? Where does it start? Do you want credit for it, or do you want to see the other person do well? It's the most selfish thing I've done in my life is give.
Welcome back. In this video, we're talking about the dining philosophers. The dining philosophers is a common problem in computer science. It's an example or an illustration of a very common thing in computers. So here we've got 5 philosophers sitting around a table for food. There is 1 fork between each pair of philosophers. So we've got 5 forks, 5 philosophers. And each philosopher has endless hunger and endless food. So let's say there is a lot of food on the table and they are extremely hungry. But in order to begin eating, 1 philosopher must have 2 forks, 1 for each hand. So as you can see, there are not enough forks for everybody to go round. So how would the philosophers tackle their problem without talking to one another? Well, obviously there is a problem, which is if each one of them picks up 1 fork. If each one picks up their left fork, say, or in this case their right fork, they then are going to wait. Then they're going to pick up the right fork and wait, and they're going to eat, put the right fork down, then put the left fork down, and then start again. But if everybody picks up their right fork, and then they're going to wait for the left fork to become available, they could be waiting for a long time, because every philosopher is also waiting for the other fork to become available. None of them releases their fork, so they all end up starving, waiting for the other fork to become available. So if the solution involves waiting for the fork to become available, they could potentially starve. So we don't want that. The problem is that if all the philosophers pick up their forks simultaneously, nobody can pick up the other fork. So they keep waiting indefinitely and they end up starving. Similarly, if any of the philosophers does manage to start eating, somehow taking up 2 forks, they may never stop eating. And so the other philosophers are forever without 2 forks, and now they've got to share 2 forks amongst 4 philosophers. That's even worse. 3 forks amongst 4 philosophers. So what can you do to solve this problem? There are many ways to solve the problem, and these are normally covered in concurrency courses, computer science degrees, so on. Not going to get into too much depth, but normally the easiest, simplest way, which is how Python itself does it, is to have a waiter at the table, like this one. So what can happen now, or the way we could restructure our algorithm, is to say that a philosopher can request 2 forks from the waiter. And the waiter will give it to them if they are available. And then when a philosopher has 2 forks, they're going to eat for a fixed amount of time. And after, they're going to return the forks to the waiter, and the waiter can then give it to other philosophers and so forth. So something like this could happen. 1 philosopher could ask for 2 forks, and then the waiter will be like, sure, take 2 forks on the table, and give them to the philosopher. Now this philosopher has 2 forks, and all the other philosophers are doing nothing. Then some time passes, maybe 10 minutes, and then the waiter will take the forks back, give them back, and I will take the forks back, and I'll put them back on the table. Now, 1 philosopher has not starved, which is good. The other 4, however, not so lucky. Instead, what could happen is something like this. We could get all the philosophers asking for their forks, more or less simultaneously. Remember, nothing can truly happen simultaneously, at least not in Python, okay? Because there is a limited number of forks in Python, let's say. So all of these people ask for the forks more or less simultaneously, but there is someone that asks for it first. So that person, let's say number 1, is the first person on that list that you see at the bottom right. The next person to ask for forks was number 2, and then 3, then 4, and then 5. So let's say they asked for them in order. So what happens then is the waiter first gets 2 forks, gives them away to number 1. Number 1 is now on a different list, let's say. Now it's on a different waiting area, on an eating waiting area, let's say. Then we still have forks available, so the waiter would take 2 forks and remove 2 from the list of waiting for forks, give them the forks, and put them in the list of, say, eating. So now we've got 1 and 2 are eating, 3, 4, and 5 are waiting. Then, number 1 finishes eating after some time, so the waiter gets the forks back. Number 1 disappears from the eating list, forks go back on the table, number 1 goes now at the end of the queue. 3, 4, 5, and then 1. Similarly, after some time, number 2 finishes eating, disappears from there and goes back onto the other list. Now, if we were to repeat this process, the next person to get the forks would be number 3, and then number 4, then number 5, and then we would start over. So as you can see, this enables each philosopher to eat, not all at once, but they all get to eat eventually. So what's happening here is that we have a limited number of resources, in this case forks. And with these resources, we can at most run 2 things at the same time, 2 philosophers. Because 2 philosophers take up 4 forks, so there's only ever 1 fork left over, and a philosopher cannot eat with just 1 fork. So it does not matter how long and hard we think, the simple truth is that there is no way that we can have 3 philosophers eating at once. But what we can do, though, is trick the mind into thinking they're all eating at the same time. If instead of giving each of them 5 minutes before releasing their forks, we give them, say, 5 seconds or 50 milliseconds, someone looking may not be able to tell that they're not eating at the same time. Very much like a movie is just a set of still images, one after another. If the passing of forks happens sufficiently quickly, we won't be able to notice that it's not happening all at once. So if each philosopher eats for 1 millisecond, it would look to an observer that they're all eating at the same time, whereas really, they are not. So remember, even if we can't see it, it doesn't mean that it's happening all at once. Okay? And in Python, this is particularly important because Python cannot run multiple things at the same time. We're going to look into this more very soon. So now that we know about the dining philosopher's problem, we are ready to move on and start looking at how things happen in Python. With that said, I'll see you on the next video.
So confidence, there's been times when I've felt I'm in possession of it, and then you want to let go a little bit because it's only ever the moment and life guiding you. The wind is so at your back that you're like, wow, are you just, jumping over the waves and all that by yourself? And you're like, you bet I am. But there's a physics to the moment, man, moment, machine, whatever, and the wind's at your back. And then the wind does what the fucking wind does, and it changes. And if you're left there thinking, so I think it's great to be in full possession of what you would call supreme confidence, and then see what happens if you don't hold on to it so hard, because it's great, but it is a bit of an illusion because like everything else, it's always changing. And every day the reset button, the space bar gets pressed, and it's like, now what?
Hi and welcome back. In this video we're going to talk about processes and threads. Processes and threads are getting into more and more complicated topics in computer science. So please use the course Q&A and also do your own research to find other ways of explaining things if anything's unclear. Processes and threads are 2 essential parts of how your computer operates, and all computers have processes and threads. Your computer has a number of cores inside it. A core is just a unit inside a computer that can perform some mathematical operations. Your computer has a processor, a CPU, like for example an Intel i7 or an i5 or an Intel Pentium or an AMD. These CPUs, these processors, have inside them a number of cores. And each core is reasonably independent, although they can communicate with one another. Each core, I mentioned earlier, is a unit that can perform mathematical operations. And by the way, that's all computers do, is perform mathematical operations. And then when you have enough of them, they can do things like print things out to the screen and, display graphics and so forth. So each core can be responsible for essentially running one thing. So going back to our philosopher example, you could have one philosopher on each core. So each core is essentially running one philosopher, which, going to our previous analogy, is that one philosopher has the resources it needs in order to eat. So here you'd have 4 philosophers, each with 2 forks, eating because they've got the forks necessary to eat. Okay. Now, of course, again in our previous analogy, we also had a number of waiting philosophers that were waiting to eat. And in computing, these would be waiting threads. These are threads or things we want to do that don't have the resources to run yet. In this case, these would be philosophers waiting for their forks, the resources, to become available. Okay. So a thread in computing, moving away from philosophers, a thread in computing is a line of code execution. For example, your Python program can run in a single thread, or a game can run in a single thread. Anything can run in a single thread. It's just the code in an application that runs from top to bottom. That can run in a thread. And you can have one thread running in one core at a time. So if you have 4 cores, you can run 4 threads at the same time, one in each core. Okay? Now, the other word inside this presentation that we wanted to look at is the word process. A process is not something that runs. Okay? What runs on the cores are the threads. But a process is sort of wrapper around it. So a process contains at least one thread, it can be more, plus some resources set aside by your computer, your operating system. So, for example, normally the process will contain one thread plus the core that the thread is running on, and potentially some other resources that it has reserved, like a network connection or a hard drive, some file pointers, or anything else. And of course, these resources continuously change as the process's needs change. For example, the process can reserve the network for a few seconds and then release it, let go of it, so that another process can have it. Similarly, a process can reserve a core to run a thread on it for a period of time, and then it can release it so another process can have it. Okay, so the thread is a thing that runs, and the process is what manages all the resources that it needs in order to run. So this is going to be important in just a moment. Let's go back and have our cores here, each running a task, and we have our waiting threads which are waiting to run. 2 of the threads in the cores could be part of the same process. Okay, so here we would have the process being the 2 cores plus the 2 threads plus any other resources that those threads need, like the network or whatever else. Similarly, you could have other processes with also some threads running and having their own resources. In this case, process 2 has a resource, which is a core, and it's running a thread. Process 3 also has a resource, which is a core, and it's running a thread. The waiting threads could be a part of one of these processes, and they just happen to be waiting, or they could be part of other processes, which at the moment don't have any resources. Okay, so the process is just the wrapper around the threads and the resources they need. Going back to our philosopher example, where we have here our 5 philosophers, we could have, in an imaginary scenario, a computer that has 5 cores. And our philosopher each needs 2 resources to run, so we could say that they need 2 of the cores in order to run. So going back to the example, here we would have again 2 philosophers running, each consuming 2 resources, and 1 resource left over that cannot be used because we don't have anything that can run on a single resource. In computers, this is normally not the case. Nearly everything can run in a single core, but some things benefit from running in multiple cores. Okay. So in computing, we have the cores, and each one can run a thread. So let's move away from the philosopher analogy. It starts to break down shortly after this. So when you have your 2 cores, each running a thread, the thread is represented here by the T, by the way, then all is good. These 2 threads can run forever. So if you just have these 2 threads and you just have 2 cores, you can run the 2 threads forever. They never need to stop running, and that's fine. An example could be one of these threads is controlling what gets displayed to your monitor, your screen, and another controls the cursor, your mouse, that gets displayed on your screen, and the fact that it can move around and so forth. So if you have these 2 threads, you can see your mouse moving when you move it, and you can see things in your monitor. And that's good. They will run forever. And of course, these 2 threads could belong to one process, or it could belong to 2 processes separately. Okay, but not to 3, because each process has to contain at least 1 thread. Now, if we add in waiting threads, which there will always be some in your computer, for example, something to deal with you typing in your keyboard, now you have to decide if you want to run the 2 threads that are currently in the cores continuously, so that you can see things on your screen and you can move your mouse, then your keyboard is never going to respond, because the thread that deals with your keyboard is waiting and is never going to run. So you have to start doing time slicing. Otherwise, the waiting threads are going to starve. And we don't want that. Okay? So time slicing, moving one thread out of a core and putting another one in. This is not free, by the way. So it requires some resources by your computer in order to do that, because the operating system has to save the current status of the thread. Remember, a thread is just a line of code that's running, so you have to save where the code currently is, so that when you bring it back into the core after it's gone through the queue, it doesn't have to start from the beginning of that code. It starts from where it left off. And this is not free. The operating system has to sort of save the status, pull it out of the core, bring another one in, and then when that's finished, remove that from the core, bring your old one in, reset the status back to what it was before, and continue running. So it's not completely free. There's some communication, there's some overhead in changing from one thread to another. But this is time slicing, and this is essentially the foundations of processes and threads, and also on how your computer operates. Over the next section, I'm really excited to guide you through how this works in Python. So let's move over to the next video. We're going to talk a bit more about that. I'll see you there.
Today, I want to talk about purpose. But I'm not here to give you the standard commencement about finding your purpose. We're millennials. We try to do that instinctively. Instead, I'm here to tell you that finding your purpose isn't enough. The challenge for our generation is to create a world where everyone has a sense of purpose.
Hi and welcome back. In this video, we're going to talk about a topic that nobody talks about in online courses, so I hope you're excited about covering this one. And that's the Python GIL, the Global Interpreter Lock. This is a pretty advanced topic, and we're not going to go into all the technical depth, but we are going to cover what it is, why it's there, and sort of what it means for us. So when you launch a Python app, you actually get a new Python process. We know now what a process is. A process is at least one thread and some resources. So the process can deal with going into a core, coming out of the core, reserving some resources it needs, like, access to a file or something like that. So you get one thread in Python, you get the main thread, but you can make more threads if you want. So when you launch your Python app, you get a thread that runs through your Python code from top to bottom, as we've seen, but you can make more threads if you want. We're going to look at how you can do that. But given that we know only a single thread can run in a core at once, why would you? What's the benefit of making more threads? Well, of course, the benefit of making more threads is so you can run one in each core. If your computer has more than one core, you could get Python to make 2 threads and run them in 2 cores at the same time. Not so fast. Due to how Python has been implemented, so the people who wrote Python, you cannot run 2 threads in one process at the same time. So if you have your Python process create another thread, the main thread and that other thread are not going to be able to run at the same time, even if you have 2 cores. And that's because each process in Python creates a key resource, a critical resource. And when a thread is running, it must acquire that resource. And every process creates only one of these. Okay, think of it like a core, except it's not a core, it's just another type of resource. The process creates this unique resource, and when a thread is running, it must acquire it. And Python is going to check that your thread has that resource before it runs it. And because there's only one of those resources, you can only run one thread in that process at once. So you may think, well, why is this resource being created? And that's a good question. We're going to go into that in just a moment. The resource in question here is called the GIL. Okay, that's the resource that the process creates and the threads must acquire. The GIL is the Global Interpreter Lock. And a lock is a specific type of resource in threaded code. So this is what the process creates, this Global Interpreter Lock. A thread must acquire it, then they can run, and then they must release it for another thread to run. So you cannot run 2 threads at the same time. Okay, so what about multiple Pythons? I mean, I'm sure you have run multiple Python apps before, and they ran side by side, right? Well, yes, you can launch multiple Python processes, like we saw just by, opening another Python app. And that's fine, because each process creates its own GIL, each process creates its own thread, but they cannot collaborate. You cannot have collaboration between processes easily. I mean, there are ways to do it, but it's not free. It's quite expensive. It takes a lot of computing power to communicate between 2 processes. That's just how computers have been designed, so that you can have separate resources in each process, and they are completely separate entities, essentially. So they cannot easily share data. For example, if you have some variables in one process, you cannot send the values of them to another process and receive responses back. It's not that easy. Whereas it is quite easy when you're doing threads. So what is the point of threads in Python then? I mean, Python allows you to make threads. What's the point of threads? Sometimes when you go to conferences or you talk with people will tell you, threads in Python, they're crap, you shouldn't use them. Because using threads is not free. It takes some computing power to, as I said in the last video, remove them from the cores, put them back in. So when you have threads, you can actually see your Python code become slightly slower. So what is the point of threads? If they can not run at the same time, and also they can make your code slower. Well, let's say you have a Python program that does 2 things. Okay, just does these 2. One of the things it does is it does a complex mathematical operation. Something that takes a long time. So let's say that thread or this operation takes a long time because it's a complex calculation. Your computer has to do a lot of things in the CPU, in your processor, in order to arrive at a solution. And it also does an entirely separate thing, this program, which is it collaborates with the user. It asks the user for some input and then it greets them, or it lets them pick something from a menu or something like that. This operation can take a long time because the user can take a long time to type. So you can see that there are two different things going on here. In number one, your computer is being used to perform calculations. And number two, your computer is not being used because it's just waiting for the user to type something. But the whole operation of asking for the input and greeting the user can take a long time because of that wait. So in a single thread, you can do one of these two. You can first do your mathematical calculation, which is going to take a long time because there's a lot of things to do. And then you can sort of interact with the user, ask them for something, and greet them back. And notice how this one is also quite a wide rectangle. That was my way of signifying that, this can take a while because the user has to type. And the user's typing normally takes a long time. So this is one option in a single-threaded code, or of course, you can do the reverse. You can ask the user for something first, and then you can run your mathematical calculation after. In either case, these threads end up taking a reasonable amount of time. This thread, single thread, ends up taking a reasonable amount of time overall. So we can instead do cooperative multitasking. But you must remember, no matter what we do, we can only run one thing at a time. So here's what cooperative multitasking would look like in Python. This is one of the exciting bits about Python, by the way. First, you would run some of the user code where you would ask the user for input. And then you'd immediately release the GIL and run your mathematical calculation. Remember, when the user thread releases the GIL, another thread that is waiting can then acquire it and use it. And that thread is going to continue running until they release the GIL. So when the user responds, this code is then going to have something in it to say, hey, if the user responds, release the GIL. So we release the GIL and we go back to the user. And here we can greet the user, which is really quick because we're just constructing a string and printing it out. And then we can release the GIL immediately and go back to running our mathematical calculation. Notice how the yellow segment is smaller now in conjunction. Because what we have removed, all that bit there, was our code waiting for the user to type. And because of threads, we no longer need to do that. Okay? Because now, our threads are only running when there are things to do in the computer. When the user's waiting, or we are waiting for the user to type, or some data to come into our program from some place, we don't have to be waiting. We can be doing something else during that time. Notice that this bottom set of rectangles would take slightly longer than just the addition of the user and the mathematical calculation because of the threads sort of communicating with one another, GIL being released, GIL being acquired, being put on the core and then removed from the core. So there would be a little bit of overhead. But overall, it would take less time than the one above. So, going back to what the point of threads in Python is to reduce waiting time. That's about it. If all your threads are doing things in Python, if all your threads are using your CPU, your processor, multiple threads is not going to help you in Python. Okay, because Python doesn't do very well that running things in parallel. And the reason this works is because the OS is going to give priority to threads that are doing things. So in this case, our mathematical calculation thread. So if a thread is waiting, it's going to run less frequently because the OS is going to realize that, there's a thread that wants to use the CPU and there's a thread that doesn't. So we'll probably run the one that does a bit more often so that it gets a bit more time on the CPU. Okay, that's it for this video. I just wanted to tell you about the Python GIL, and now you know that you cannot run two threads at the same time in Python under the same process. But there are things you can do in order to make your code more efficient with the use of threads if your code involves waiting. That's it for this video. I'll see you on the next one.
You know, I don't think anything changes. In my humble opinion, I feel that's a mistake that a lot of people make, that with more success comes more responsibility, and so you have to start changing things in your life. I actually look at it the other way, which is you are where you are because of certain things that you've done or certain things that you've believed in. So to remember your roots and to go back to and keep reminding yourself of why you are here. And what is it, and what are those decisions, or what are those thoughts, or who are those people who have helped you get to where you are. That's the way I look at it.
Hi and welcome back. In this video, we're going to look at a couple example codes from what we covered in the last one. So I've created a new project in PyCharm. I've called it concurrency. And we're going to create a new file in here, a new Python file that I'm going to call threads. Okay, by the way, this code is available, linked at the start of the section, which is on the GitHub for this course. So let's say you've got some code that you want to run, like we saw earlier, that asks the user for something, and then some other code that does a complex calculation. Okay, we're going to have two functions. The askUser function. This is going to, get some input from the user. And then it's going to construct this greeting. And finally, it's just going to print it out, greet. This is what this function does. And as you know, this function here is going to wait for the user to type something. Okay? These functions here, or these statements here, are not going to wait for anything. We'd say that this is a blocking operation, okay? An operation where your thread is blocked, waiting for something to happen. So these operations are what makes your threaded code slow, okay? Don't worry about that too much. We're going to explore this concept more and more over the coming videos. Then you're also going to have a complex calculation function that is going to do something like print, started calculating, and then it's going to do something that takes a while. It's just going to do something pretty silly. X to the power of 2 for x in range 20 million. Okay, 20 million? Yeah, 20 million will do. So this should take about 6 or 7 seconds in my machine. It could take longer or shorter in your machine. Just tweak the number accordingly. Okay, so it's going to do that. And that's it. Then we're going to do askUser first. And then we're going to do our complex calculation. Now, of course, we're not going to know how long they take unless we start timing them. So we're going to import time at the top. And all I'm going to do is every function time it. So we're going to do start equals time.time. And at the end, we're going to print askUser time.time minus start. Okay. Same thing for the complex calculation. Now, I'm also going to do this for the whole program. So I'm going to track how long the whole program took. Like that. Okay. Again, all that's happening here is, first of all, we start a timer. Then we launch the askUser function, which starts a timer inside that function, asks the user for some input, waits for the user to type, constructs a new string and prints it out, and then it's going to print the end time. Then it's going to launch the complex calculation function, which is going to start a timer, print how you started calculating, go through this list comprehension, which is a pretty massive one. When it's done, it's going to print out that the complex calculation took a certain amount of time. And then at the very end, we're going to print that the single thread took some amount of time. You know from all the Python development we've been doing up to here that this is going to run from top to bottom. You know, this is going to run first, and then this one, our execution is going to jump to here, then here, then here, then it's going to go back, and then it's going to go here, and so forth. This is a single thread. This is our normal Python runtime. We sort of write our code, and it runs from top to bottom, because the thread is this line of execution that we've given to the CPU core to run. So if we run this file, if we run threads, the first thing it's going to do is ask me my name. I'm going to type it in. Oh, and I think I put one too few zeros here. Didn't take long enough. Notice how the complex calculation took 0.6 seconds. I want it to take 6 seconds, so I'm going to run it again. So types my name, and it took 1.6 seconds to run the ask user function, and then it started calculating. And it took about 6.4 seconds to run the complex calculation. And in total, it adds these two together essentially, plus a little bit of time, not a lot of it, but a slight amount. This single thread took 8.14. The slight amount extra it takes is because, it has to jump from here to up to the function and so forth. That takes a couple nanoseconds. So it's not going to be an exact addition. But, overall, it's sequential. First we ran this, then we ran this, and the total is more or less the addition of both. Okay. Now, what we're going to do is I'm going to collapse these functions. This does not delete them, it just hides the code in them, so it's a bit easier for you to see. They're still doing the same thing, okay? And what we're going to do then is from threading, import thread. So we're going to import the thread class from the threading module. The threading module comes with Python, you don't have to install anything, and this gives us access to threads. Whenever we create a thread, that's going to go to the operating system, and it's going to ask the operating system to give us a new thread. And the operating system is going to be like, okay, here you go, new thread. You can run whatever you want in it. And what we're going to run is we're going to say thread 1 is thread, and the target is going to be our complex calculation. Notice that the target is the complex calculation function, not the result of it. So we're not going to run the function here. We're just going to pass it into the thread. And when we ask the thread to start, what it's going to do is it's going to start a new thread running just this complex calculation. And thread 2 is going to be a new thread where the target is the ask user function. Okay. So now we have 3 threads. A main thread, which is responsible for running through the app. A thread which is responsible for running the complex calculation. And another thread which is responsible for running the ask user function. So we're going to run these two at the same time, and we're going to see what happens, okay? So the first thing to do is to do time.time, measure the start time. Thread.start, thread 1.start, thread 2.start. Now these threads have started, and they are running at the same time as our main thread. Okay, so now we have 3 threads running at the same time. When we start this one, the complex calculation function is running. When we start this one, the ask user function is running. And also our main thread, which is responsible for running this code, is also running. So we have to tell our main thread to wait for these 2 threads to finish. The way we do that, thread1.join and thread2.join. This tells our main thread to wait for thread 1 to finish and wait for thread 2 to finish. Again, these here are what we would call blocking operations, because they're making this thread wait until something happens. But in this case, we want to do that because we want to wait until the threads finish before we can calculate the end time of the thread. So we're going to say toThread total time is time.time minus start. Okay. This is fine. Don't worry about that yellow thing. Let's run this again and see what happens. What do you think is going to happen? Think about it before we continue. Ask me for my name, took a couple of seconds to do that, then it starts calculating. And in the end, it's going to take more or less the same amount as before, 8 seconds. Then it asks for my name again. It took a little bit longer now, just to type. But notice how, in total, it took 6.45 seconds instead of 8.36 seconds. But the complex calculation took essentially the same amount of time. The ask user took even longer. But this is fine, because in total, we took as long as the longest running function. And that is because the askUser function didn't do anything except wait. Okay? The difference between these two times is how much CPU the askUser function needed, plus how long it took us to switch between the threads in the CPU, in the processor, in your cores. As you can see, not a lot of it. In total, the two-threaded time took more or less the same amount of time as your complex calculation, because your askUser function didn't actually need the CPU for anything. It just created a new string, and that's it. So hopefully this makes sense. This is what threads are for. It's for reducing waiting time. When you have a blocking operation, like this input, that is waiting, making your program wait for something, that's a good use for a thread. If you have a function like this complex calculation, using a thread is not such a great idea. And here is a final example for you. In our threaded code, I'm going to not use the askUser function. I'm going to use the complex calculation function again. So now we'll have two threads, both running the complex calculation. Separate instances of it, but they're both going to calculate the same thing. Okay, let's run this again. It'll ask me my name first because that's the single-threaded code. And now let's see what happens with our calculation. Remember, only one thread can run at a time. Okay, so you cannot run both at the same time, but we get started calculating twice because this is two functions that are running, each in one thread. And now let's see what happens. Notice how it's taking a while. There you have it. Complex calculation now took double the amount of time to run because they cannot run at the same time. So the operating system was sort of giving a little bit of time to one, then pulling it out and giving a little bit of time to the other, then pulling it out and going back to the first one, then going to the second one, and so forth, switching between the two. But all of them needed all that time in the CPU to calculate things. So in total, what you did is you spread out the time that each one was running, and you sort of interspersed one with the other continuously, and in the end it took double the time. If you had run these sequentially without threads, it would actually be faster because you wouldn't have to deal with removing one thread and putting another one in. So if you are doing things that require the CPU all the time, don't use threads. It's pointless in Python. There are other ways of doing similar things, as we will learn, and that could be better. Now we're going to go back to our askUser function here. Again, this code is available on the GitHub. Please download it, play around with it, run it, make a few changes, have a think. This stuff is complicated stuff, okay? There is a reason why not many courses go into this, because it's difficult. And I am expecting you guys to come to the course Q&A and ask questions, and, I'm here to help you out if anything is unclear. So please do use that resource. I want you to leave this course knowing about this stuff. So that's it for this video. Thanks for joining me in this one, and I'll see you on the next one.
The first thing I want you to take away from today is this: you will have good days and you'll have bad days, but you will always learn something more or something new, and you will learn more overall on bad days than good days. You will learn more about yourself, you'll learn more about relationships, you'll learn about life and principles, and it'll build your character. If you're a person who wants, let's say, improve on your character of patience, let's say, don't complain when you're waiting in a line. You ain't going to grow in patience until you're put in a place to wait.
Hi and welcome back. In this video, I just wanted to tell you a little bit about the concurrent.futures module and how it can make our threaded code a little bit nicer. Here we've got some code that creates threads, starts them, and then waits for them to finish. What you can do instead is you can create a bunch of threads with no target, then give them a target, start them, and join them. So the reason for that is if you were to create a bunch of threads with no target, then you can choose which thread is going to take which job afterwards. And it doesn't really matter which one does, but essentially you end up with sort of a collection of threads that you can send a task to and get a result back from. The reason for that, the reason to do that, and I'm just going to delete that code, is to just make your code a little bit nicer. So instead of importing thread from threading, we're going to do from concurrent.futures import ThreadPoolExecutor. ThreadPoolExecutor is going to create a pool of threads, that's just a bunch of threads with no target. And it's going to allow us to use that pool to execute jobs, or in this case, our functions. Okay, so with ThreadPoolExecutor and max workers is 2 as pool, all we're saying here is create 2 threads in this pool of threads, in this collection of threads. Then we can say pool.submit, complex calculation, pool.submit, ask user. And that's it. Our code has been simplified slightly now. Again, this creates a pool of threads, a collection of threads, and then we can submit a task to it. And because we've used it with this with statement, all this does is it waits for the pool to finish. That essentially means we don't have to call pool.shutdown. Okay, pool.shutdown will normally wait for these things to finish. And this is again a blocking operation. But if you use the with, you don't have to use pool.shutdown, so it just makes your code a little bit nicer using this context manager here. ThreadPoolExecutor and generally the concurrent futures module is very popular, and as you start advancing in your Python journey, and you, for example, go to conferences or you listen to talks on YouTube or things like that, you'll see the concurrent futures module mentioned every now and then. ThreadPoolExecutor is a pretty popular thing, just to have a bunch of threads waiting, and then you can sort of ask them to do something and get a result back, ask them to do something, get a result back, without having to be always creating new threads. So that's why you'd have a thread pool there, to save yourself from creating new threads all the time. Okay, that's it for this video. Just wanted to show you this ThreadPoolExecutor, and I'll see you on the next one.
Run toward all of the things that you're afraid of in a truthful way. Contend with it with an open mind. I think that's very, very important.
Hi and welcome back. In this video I just wanted to tell you a little bit about killing threads. I've gone back here in the code to the code before using the ThreadPoolExecutor, and we notice that we've got thread1.start and thread2.start. Then we've got space to write more code, and then we wait for them to finish. Inside this space here, you could write some code to kill the thread. For example, if it meets some criteria, or maybe you no longer need it or something. You could write some code to kill the thread. But you should not do that. Okay? Don't kill a thread. Wait for it to finish. If you kill a thread manually without being really careful, what can happen is that your thread has acquired the GIL. You kill it before it releases the GIL, and then what you've got is the GIL is gone. Okay? No other thread can pick it up because it wasn't released before. Threads will not release the resources just by killing them. You need to release the resources manually in the thread code itself. Okay, so if you have your thread and it started and it's using the GIL and then you kill it, the GIL is gone, no other thread can get the GIL, your Python program will stop. It won't terminate because the thread here will be waiting to finish, but it won't be able to do anything. And if that happens, if you have a resource that's being used and nothing else can use it, this is called a deadlock in computing, and it's a bad thing, okay? So just be careful, don't kill threads. That's just all I'd say. Don't kill threads, it's not easy to do. I don't recommend it. If you kill threads, you're going to have problems, so don't do it. That's it for this video. I'll see you on the next one.
I think anyone who's in a field doing something that they truly love, it never feels like work.
Yeah.
And you feel a sense of liberation and freedom in doing that. You know, it could be any job, a corporate job, you're dancing, you're an athlete, anything, an actor, whatever it is.
Hi and welcome back. In this video, we're going to talk about launching multiple processes. So you can launch multiple processes with Python. You can have your main Python process that gets created when you launch your Python app, and you can ask your Python code to launch another process. When you do that, each process can have its own thread running in two separate cores. Okay, so the two processes will be entirely separate from one another. As part of doing that, it can also set up communication between the processes, and that communication is slow, but it can allow us to run two things actually at once in two separate cores. It's not entirely that simple. Let's have a look at some code. Okay, I'm gonna copy some things from the earlier section here. Oh, sorry. Let's copy from here. So I'm going to copy all of this, and I'm going to delete the thread code in here, and I'm going to delete that. So what we've got are our two functions, ask user and complex calculation. Once again, we've got our timing functions, and we're going to ask the user first, run the complex calculation second, and print out how long that took. If you want to have multiple processes, you can do that. All you have to do is say from multiprocessing, import process. Now you have the process class from the multiprocessing module, and you can use that to launch a new process. Let's do it. We're going to say the new process is process, target is complex calculation. So that's going to be the target of this process. And then we're going to say process.start. We're going to say start equal time.time. We're going to ask the user for something. We're going to wait for the process to finish running. And then we're going to print, to process total time is time.time minus start. Okay. Very similar to what you would expect from the thread code processes. You've got your new process, you give it a target, you start it, and then when you want it to wait until it finishes, you do .join, and that's it. Okay. Very straightforward. Let's run it and see what happens. Let's right-click the processes file and run it. Asks me for my name first, then it starts calculating. And then it's going to ask me for my name again. And notice how that's sort of screwed up. That didn't look so good there. Yeah? And again, it took me a bit longer to type in my name now because this was a bit messed up. But it took the same amount of time as the multi-threaded code. Some would say it takes a little bit longer. It probably does take a little bit longer because creating a new process is a bit more expensive than creating a new thread. But generally, it works. Yeah? This thing here, though, enter your name, started calculating, ... is a symptom of the problem. And the problem, we're going to see it when we try to do something else, which is now I'm going to create another process for my ask user function. So process 2 is going to be process, and the target is going to be ask the user function. Then we're going to start process 1, we're going to start process 2. We're not going to ask the user anymore in the main process. We have now two processes for that, and we can do process2.join. Okay. Same thing as before. We create our processes, we start them, we start the timer, now we wait for them to finish. But you'll see that this won't work so easily. Let's run this again. Go at the single-threaded code first. Starts calculating, and then when it finishes, it's going to launch my two processes. But alas, we get an error. And sometime after, we'll get the complex calculation finish. So here, the problem is that we get an EOF when reading a line, end of file when reading a line. Our process could not run this input function. And the reason the process could not run this input function is because it doesn't have access to this terminal here. Remember, the processes cannot share resources very easily, so it doesn't know where we're meant to be reading from. When we tell it to finish by doing process2.join, it says, okay, you didn't type anything. There was nothing. There's no way for me to get the input, and also there's no way for me to type it. So, finish the process, and you get an error there. There's no place for me to type the input because it doesn't have access to this thing that I was about to type. And so a bit of a strange problem there, but this is the reason why earlier on you got your two lines in the same line. They were accessing the console simultaneously, but it was essentially a separate entity. So a bit of a complicated thing. Using processes is not easy, okay? Because they are separate, you start getting sort of separate resources, sometimes duplicate resources. One of them doesn't have access to something, the other one does. So, not terribly easy to use processes. Normally, you'll use processes if you have a multi-core machine, like my laptop is, and you want to do complex calculations on both. So if you want to do that, you can do that. You can run the complex calculation on both machines. Now you won't get this error. Let's run this again. And let's see what happens. This is the single-threaded code, by the way. It took 6.47 seconds. Then we started calculating twice. And now we're hoping the operating system has given us 2 cores to run this in, and it seems like it did. And now the 2 complex calculations ran in a longer amount of time, close to 7 seconds now instead of 6.47. But they ran both at the same time. This is why you use multiprocessing, when you need 2 things to run at the same time in the CPU. If your problem is you have things that are waiting, like this user input here, you don't need multiprocessing. What you need is multi-threading, and you want to, have cooperative multitasking between the 2 threads. So this is multiprocessing. Just wanted to show you quickly when to use it and when not to use it. And we're going to be encountering a couple more scenarios of where we want to use this later on in the course. So that's it for this video. I'll see you on the next one.
You need a vision for your life. Vision is the ability to look into the invisible and to create and to see that which does not exist. I was thinking about my life. So much of the good things in my life were birthed out of vision. Like, I got married because I had a vision. I remember I was 17, man, I was just kind of getting right with God. I was still learning to hear his voice, but I'm telling you, when I saw Dawn Cherie Lene Duron, Jesus spoke clearly. I said, that's the one right there. Now, it took me a while to cast the vision to her, but your boy's not too bad of a leader. I can describe a vision all day. I got that girl. Hey, okay. Some of you dudes, you better cast a bigger vision, man.
Hi and welcome back. Again, just a short video on the improvements you can make to this processing code, multiprocessing code. Instead of using the multiprocessing module, you could just use the concurrent.futures module. And you can import a ProcessPoolExecutor. Same thing as a ThreadPoolExecutor, only it creates processes instead, and the actual process is going to be exactly the same. So we're going to delete these 2, and these 2 here, and we're going to say, with ProcessPoolExecutor, max workers is going to be 2, because we have 2 things we want to run, as pool.submit complex calculation. And then we're going to duplicate that, and that's it. Okay, just a little bit simpler code. If you want your pool to stay alive throughout your entire program and maybe, submit a task, get a result back, and bring the process back into your pool of processes so that you can reuse it, you can do that with a ProcessPoolExecutor. All you have to do is not use with. Instead, define it as a variable, and then you can submit tasks to it and wait for them to finish. And the process will go back into the pool so that you can reuse it. So if you have a larger application, it could be interesting to create a few processes at the start so that you don't have to constantly be creating new processes, because that can take a few milliseconds. So that's just a potential performance improvement. nothing you have to worry about for now. Anyway, I just wanted to tell you a bit about how to use this ProcessPoolExecutor, because again, it's a very popular thing when you're doing multi-threaded code. Suddenly you encounter that, you have to do two things at once because they both need the CPU. What you'll normally do in multi-threaded code in that case is you will then submit a task that requires the CPU over to a ProcessPoolExecutor so that it can run in a separate core and then bring back the result. Okay, so using ProcessPoolExecutors is actually quite common in multi-threaded code when you need to do that in two cores. Not so common to run complex multi-core applications in Python because it's just not that good for it. Okay, that's it for this video. I'll see you on the next one.
Don't involve yourself in drama and negativity. There's nothing that depletes your creativity more than meaningless bickering and useless conversations about others. So much is destroyed and lost when we use our energy like this. Just go past that stage. Vibrate higher. Use your energy to heal, not hurt.
Hi and welcome back. In this video, we're going to look at running multiple threads at once and sharing some state between them. Okay, so I've created a new file which I've called nonlockedthreads.py. But before we start writing some code, I just wanted to sort of tell you about something, and that is, what is an atomic operation? Atomic operations are very important when you're doing multi-threaded code. An atomic operation is one that cannot be interrupted in the middle of it. So you cannot interrupt an atomic operation halfway through it by changing to a new thread, okay? Whenever you're doing an atomic operation, you know that it's going to finish before you can unplug the thread from the core and put another one in. For example, a print statement cannot print only half the line and then be interrupted. Similarly, appending to a deck, or a DQ if you're like me and you like saying that, appending to a deck cannot be interrupted halfway through. If you start appending to a deck, you say, deck.append, you know that the thing will be appended to the deck before you remove the thread from the core. Okay, so atomic operations are very important when you have this shared state between threads. Okay, and we're going to look at an example of where we're going to have a function that's not atomic and why that poses a problem. Okay, so let's do that. I'm going to do, from threading import threads, I'm going to use good old threads instead of the ThreadPoolExecutor just for this. I think it's going to be a bit easier to see what's going on. We're going to import time, and we're also going to import random because we're going to be randomizing some things. Then we're going to have a global variable in our file, which is going to be 0. Okay? And then we're going to have a function called increment counter. And what this is going to do is it's going to say global counter, access the global variable counter, do counter plus equal 1, and then print new counter value is counter. And then it's also going to print a few lines just so we can separate new counter values from one before the other. Now, from what we know about single-threaded code, if we do for x in range 10, and then we do increment counter, what do we think is going to happen? Hopefully you send, what I'd expect is that you'll start up here. X will be 0, it's going to run 10 times. The first time you're going to go into increment counter, you're going to access global counter, which is going to be 0. You're going to increase it by 1, so it's going to be 1. You're going to print out new counter value is 1. You're going to print out these lines. Then you're going to go back to the end of the function. You're going to repeat your loop. You're going to go in here again. Counter's going to be 1 now because it was increased before. Then you're going to increase it by 1, going up to 2. You're going to print new counter value is 2, and so forth for 3, 4, 5, 6, 7, 8, and so forth. So let's run this non-locked threads, which is not using threads at all, and you can see that that is indeed what happens. You get 1 all the way down to 10. So, good stuff. This is what we would expect. Now, what happens if we make a thread? We say t equals thread, and the target is increment counter. And then we're going to remove this increment counter, then we're going to do t.start. What do we think is going to happen when we run this? let me tell you that we're not going to see any difference. Okay? We get 1, 2, 3, 4, 5, 6, 7, all the way up to 10. Okay, so what was the purpose of threads, and are they running at the same time? Using or writing multi-threaded code is dangerous because you may not see the problem straight away. The problem may only appear under some circumstances. And here is where time and random are going to come in. What we've got here is 10 times we're going to repeat this block of code. We're going to create a new thread. The target is going to be increment counter. And then we're going to start the thread. And then immediately we're going to move over to the next thread and we're going to start it. But this function is so quick to run that before we get to start the new thread, that function is already finished running. So essentially this is sequential code. Essentially it's single-threaded code. Because you create a new thread, you started, by the time you create a new thread, that one's already finished. So essentially it's happening one after the other. What we're going to do is we're going to do time sleep random.random. Okay? We're going to put some time sleeps in here, essentially between each line. Like that. This technique of adding random sleeps between statements when you're doing multi-threaded code is called fuzzying. It's very popular because it's going to let us see problems. Okay, let's run this file again. Ooh, that's not looking so good now. So as you can see, what happened here now is that all our threads were running at the same time. Because, one of them started, then it encountered this random sleep. By that time, another one had maybe started and encountered another random sleep. You've got a few of them starting, some of them are here, some of them are here. And what happens is, you've got a couple of threads getting the counter value as 3 and increasing it by 1, both at the same time. Okay, so you've got 2 threads coming into the global counter. 2 threads are stopped here. The counter is 3. Then they both increment counter by 1 at the same time. So it ends up as 4. And then they both print out new counter value is 4. Okay. So multi-threaded code with shared state can be really tricky to get right. Because 2 threads can try to access the same thing at the same time. And that's fine. You can access the same thing at the same time. But you may not end up with what you'd expect. Particularly if all the threads are changing something in this variable at the same time. And you may not see that unless you do this fuzzying technique or, other techniques. So what we've got here are all our threads running, they're messed up, essentially. We cannot proceed with this. And if you remove the fuzzying, it will work until, your computer is running slowly, or you've got a bunch of things running at the same time in your computer and these threads are jumping in and out of course very quickly. Then you may start encountering problems like this one. So, you must be careful when you write multi-threaded code. You must be very careful. Especially if your threads, or really only if your threads are modifying shared state. Here the variable is the shared state. These threads have that variable shared amongst them. Dangerous stuff, okay? This code, by the way, and also the code that follows, is taken from a talk that one of the Python developers, the creators of the Python language, made. I'm going to link you to this talk at the end of this section. So it's really good. I just want to guide you through it first, in my words, just to help you understand it, and then you can go and watch their talk later on. Okay? If we wanted to make sure the operations happen sequentially, like we want to do new counter value is 1, then new counter value is 2, then 3, then we would have to do something much more complicated. But again, if you want to make sure the operations happen sequentially, don't use threads. That's the first thing. If you want to make sure the operations happen sequentially, but you want to use threads, then you have to set up a queuing system where each thread can perform the operation of incrementing the counter, but they happen one by one. And so it's going to be more complicated code. Let's go over it in the very next video, how you may do queuing with the threads so that the operations happen sequentially. I'll see you in the next video.
It's Saturday night, 1:45 a.m. I just wrapped a phenomenal workout here in the Iron Paradise. Got after it hardcore. Hardest workers in the room. We just wrapped here in the Iron Paradise. Another great workout. Iron ain't gonna kick its own ass. You gotta get after it. Let's roll. You reach that point, we all reach that point where we're training, and you break through to the other side. You break down barriers. You bust through ceilings. You knock down doors. That just happened for me. It's very defining. I've been slinging iron since I was 13. Our empty gym, the way we like it. It's Sunday, it is family day, it's Lord's Day, it is also leg day. So, this pain ought to be fun. Shit, happy Sunday. And in the moments where you push yourself, when no one else is around, those moments have a tendency to lead to success.
Hi and welcome back. In this video we're going to look at something substantially more complicated. So please stay with me and let's look at queuing in threads with shared state. The first thing I'm going to do is import a few things. So I'm going to import time and random, as we know, to do our fizzying. And I'm also going to import queue. The queue module has a queue in it, which is going to be essential for our program to work. And I'm going to explain exactly what this queue does and why it's different from a deck. And then, of course, from threading, we're going to import thread to start with. We'll then use a ThreadPoolExecutor later. We're going to have our global counter. And we're also going to have two queues. We're going to have a job queue. And we're going to have a counter queue. Okay. Job queue is going to be the command, the things to be printed out. The counter queue is amounts by which to increase counter. Okay? All right. Now, we are going to be doing something, which is every time we want to increase counter, we're going to put 1 into the queue. So we're going to put the number 1 into this queue. Then we're going to have some code looking through this queue, and whenever a number appears, it's going to increase counter by that amount. At the same time, we're going to have another thread going through this job queue, and whenever it sees something appear in there, it's going to print it out. That's essentially how this program is going to work. So, let's do it. We're going to first define our increment manager, which is going to take in our global counter. Remember, multiple threads could be doing this at the same time. And then we're going to do while true. It's going to get the counter from this counter queue. Remember, this counter queue here has a queue of multiple numbers potentially by which we want to increase the counter. So increment is going to be counter queue dot get. Okay? And this is important because this waits until an item is available and then locks the queue. Okay? So this is going to wait until an item is available, and when it is, it's not going to allow any other threads to get anything until we are done. Then we're going to say old counter is counter. Counter is now old counter plus the increment. Then we are going to put something into the job queue. The new counter value is counter. And we're also going to put in our lines. Okay, we're going to put these two things. And finally, counter queue dot task done. This unlocks the queue. So now another thread could go back and get something if they wanted. So as soon as something comes in here, this counter queue is now locked. The thread has that resource. No other thread can access this resource until we call task done, and that marks the queue as not locked anymore. Another thread can then go through this get. Okay. Cool. We're going to run this target is going to be the increment manager, and daemon is going to be true. And what this means is this thread is going to run continuously forever until until it finds an error, essentially. And then we're going to start that. Okay. So this thread is going to run forever, always, while true, always checking this counter queue, trying to get a thing. It's going to wait until an item is available, and it's going to lock it, and then it's going to go through it, and then it's going to call task done, then it's going to repeat. Again, it's going to wait for something to become available, and so forth. Now, if we want to print, we're going to create a printer manager. Just going to scroll down here. Again, this is going to be while true. It's going to get the lines in the job queue for line in job queue.get. And again, this locks the queue and waits for an item to be available. It's going to print the line out. And at the end, it's going to be job queue.taskDone. Okay. Once again, we are going to run this as a daemon thread. And we're going to start that. Okay, so the printer manager and the increment manager are going to run continuously because of that daemon flag. The final part of our program is to deal with increasing the counter itself. So this is going to be running constantly, getting values out of counter queue and increasing the counter by them. This is going to be running continuously, printing things out. All we have to do is to put something into our queue. So let's create another thread or another function that is going to be our increment counter. And this is all it's going to do is do counter queue.put 1. It's going to put the number 1 into the queue. Then it's going to get received by this increment manager, which is going to increment the counter by that amount. And it's going to put 2 things into the job queue, which is then going to print them out as it runs. Okay. Then we're going to make a few worker threads. Worker threads, these are going to be threads where the target is this increment counter. For thread in range 10, we're going to make 10 of them. And then all we're going to do is start them. So for thread in worker threads, thread start. And we're going to wait for them to finish for thread in worker threads, thread.join. And at the end, we're going to wait for the counter queue to finish, to not have anything left in the queue, and the job queue to also not have anything left in it. Notice how we are joining the queues, not the daemon threads, because the daemon threads are never going to stop. They're always going to be running, okay? So we're joining on the queue. When they become empty, we will essentially be done. As you can see, this is substantially more complicated. Now that you have shared state, you have to start having queues in there so that your threads cannot interrupt one another. Let's run this code and see what happens. Oh, I forgot a pair of brackets. What you put in the queue has to be a tuple. My bad. Let's run this again. And there you have it. Now you get your code that looks sequential. Okay. Again, you could just not use threads and it would achieve the same purpose. But if you wanted to use threads, you'd have to use these queues. And indeed, if you add the random waits, which we will do, you'll see that this still works. So we're going to add these waits everywhere. Like there, we're going to add some here. We're going to add some here. We're going to add some here. And then we're going to run it again. And you can see that now we are waiting for our code to sort of go through this queue, but only one thread is able to go through this increment at once. So these still happen one by one. So not terribly simple, let me tell you that. Not terribly simple. Again, you could use a ThreadPoolExecutor to improve this code down here if you want. We're not going to get into that, but the code in the GitHub does have this in there. So again, just to recap, what happens is we say we're going to access this global counter variable. It's essentially just to tell Python that we don't want to create a new variable called counter. We want to use the global counter. In here, by the time we access the counter's value, this has already prevented two threads from doing that at the same time. So get waits until the item is available and then locks so that only one thread can execute this at a time and get a value out. If you have 10 threads calling this, only one is going to be able to use that resource. The other 9 are going to wait until task done is called and this becomes available again. So you've got a single thread getting the increment, which is 1. Then you access the current counter's value, which will be 0. Then you'll increase it by the increment, which is 1, make it 1, and put these two things here into the job queue. Then task done. So you go back to the top and another thread is able to do the get. When they access the counter value, that's 1 now because the previous thread already incremented it. And then you can increase it again and so forth. So essentially what you're doing here is you are creating this bottleneck for threads to only be able to access the resource one at a time. Okay? Again, this is essentially single-threaded code, but it goes to show that when you need threads to share state, you need these queues. Think of the printer in your office if you have one. The printer in your office can receive jobs from a lot of different people at once, but it can only print one at a time. So that's what we've got here. We've got a queue of print jobs, and the printer is then just continuously printing them out as soon as it sees them, but it doesn't do that all at the same time. It does them one by one. Similarly, because we're accessing a unique resource, the counter, we also must do that one by one. If we get two things incremented the counter at once, we saw what happens in the last video, they just sort of go mental and they start changing it all at the same time. If you got your printer to print two things at once, you can imagine how that wouldn't go so well either. You'd see sort of words from one document and words from another all printed together. It wouldn't be pretty. When you want a shared resource, you must use a queue. And the queue.q package here, the queue package, is good because it has this locking thing and this task done thing. So this is made for multi-threaded access to a queue. The deck, which is something that is atomic, does not get interrupted when you add or remove elements from it, but it also does not lock. So you can have multiple things appending things to a deck at the same time. And that can be handy in other situations, as you'll see from the talks that I'll link to you later on. That's it for this video. Hopefully this didn't melt your brains, and I'll see you on the next one.
I think it's the fear of losing everything. You know, I've built everything with, coming from a very middle class background, coming with 550 rupees in the Bank of Maharashtra in your account, and coming to where I've come to, wherever little I've come to, there's always this fear in a middle class guy's head that he may lose everything and he may go back to where he started from.
Hi and welcome back. In this video we're going to look at how to do multiple things at once, or sort of at once, without using either threads or processes. As you can see, I've created a file here called generators.py, so that should give you a hint as to what we're going to try to do with this file. We've looked at generators before. Let me create an example of a generator. This one is going to be called countdown. It's going to take a number that we're going to start counting down from. And we're going to say while n is greater than 0, and we're going to yield n. Remember, that gives the value back to the caller, and then we're going to subtract 1 from n. So if we have a countdown like c equals countdown that starts from 10, we can then do something like print next of c. This is sort of nothing new here. What this is doing is we're creating a new generator, and as soon as we call next, it starts running the generator and it goes up to the yield, and it gives back the value that we yielded. So in this case, it's going to give back 10. And then when we print next again, it's going to continue running all the way back to the next yield. So instead of going for 10, it would start with n as 10, it would subtract 1 from it, then it would repeat the loop, and it would yield n again, which would be 9. So as soon as you arrive at the yield, the correct word here is the function is suspended. So when you arrive at a yield, you get the value that was yielded and the function is suspended there. And then when you call next again, the function resumes. So it's very similar to a thread, really, if you think about it, because the thread can at any point be suspended or removed from a core, and then it can be brought back and it continues running where it left off. So a generator actually behaves fairly similar to a thread in that when you arrive at a yield, you're removing it from the core if you wish, and then when you press next, you're sort of bringing it back and it continues running. So let's run this file. I'm going to right-click generators.py and run it. And as you can see, we get 10 and 9, which is what you sort of expect. The first next gives you the 10. Then when you go next again, it continues running up to the next yield and it gives you 9. So this is all good. What if we had C1, which is a countdown from 10, and C2, which is a countdown, say, from 20? Yeah? Now you have two tasks. A countdown that starts counting down from 10 and one that starts counting down from 20. And what you could do is this. So here you're printing the next value of C1, goes up to the yield and gives you 10. Then you're printing the next value of C2, which goes down to the yield and gives you 20. Then you could do this again, which resumes C1, subtracts -1 from n, goes and repeats the loop, and now gives you 9. That suspends, and then you move over to the next line, which gives you the next of C2. So that instead of being 20, now you subtract 1, and you repeat, and you now yield 19. Let's run this. You can see that this is what's happening. You are running one task, then you're suspending it, and you're running another, and then you're suspending that, and you're going back to the first one, then you're suspending that and going back to the other one. This is essentially some very slow multi-threading, but without using threads. Notice there's no import of threads or anything here. What you've got is two tasks yielding control of the main thread to one another. Think of it as passing the baton in these races. So if we can do this really quickly, if we can do C1 and then C2 really, really quickly, it may look as though they are running at the same time. This is essentially the purpose with threads. Remember, you cannot run two threads at once in Python, but you can slice their time on the CPU quickly enough that it looks like they're running at the same time. So this looks a bit like a hack, like something that shouldn't really work. But actually, asynchronous development in Python is built around this generator. Not this generator specifically, but generators as a whole. So let's look in the next video at how we can build our first task scheduler using generators instead of threads. I'll see you there.
You have to have an emotional investment in what you're doing. If you don't love what you're doing, failure is pretty much guaranteed. Success is not guaranteed by any means, but failure is much more likely if you don't love what you're doing.
Hi and welcome back. In this video, we're going to be constructing our first task scheduler using generators instead of threads. Previously, we created a bunch of threads and we started them, and there was a task scheduler in the background, the operating system, bringing in threads to a core and removing them from the core. Now we're going to do the same thing, but using a generator instead. By the way, the code I'm about to show you here is partially taken from another talk by David Beasley, which is a fantastic guy. I'm going to link you to a couple of his talks afterwards. But I wanted to show you again in my own words how to do this, just to help you understand. So threads are not performing so well in Python with the communication overhead and the GIL issues. But using generators is another way of achieving multitasking, doing multiple things at once in Python. But again, remember, multitasking is doing things that look like they're happening at the same time, but they are really not. Parallelism is about doing things actually at the same time. And in Python, we cannot do parallelism because of the GIL, unless we launch multiple processes. So here we've got our countdown, and what we're going to do is we're going to create a set of tasks. So here we've created 3 tasks that are all similar. They're all this generator. Countdown from 10, a countdown from 5, and a countdown from 20. But now we can start providing them slices. Instead of on a core, we can start providing them slices on the main thread. So while tasks, this just means while it is not empty, we're going to do that the task is tasks 0, that's the first task in here. We're going to remove the task from the list, and then we're going to try to do x is next of the task. We're going to print x, and then we're going to append the task again. Okay, so all that we're doing here is we're going to get the first task in our list. We're going to remove it from the list, so our list is going to end up as these 2 tasks. We're going to create a new variable x, which is going to be the next of the task. So in this case, 10 for the first one. We're going to print it out, and then we're going to append it over to the end of our list again. If we encounter an except on stop iteration, remember this is what gets raised when we run out of values of a generator, then we're just going to print task finished, and that's it. When we print task finished, because we try to get the next value of something but it fails, we are not going to append it back to the task, okay? When we try to get the next and that gives us a stop iteration, we will not run either of these 2. All right, let's run this file. And as you can see, we start at the top with 10, 5, and 20, and they go down one by one until you see task finished, that's the 5. Then you see task finished, that's for the 10. And then the 20 sort of takes up all the time in the CPU, or in this case, in the main thread, and eventually finishes as well. Notice that these tasks are quite simple. They don't really do much. But this is an example of multitasking in Python without using threads. You've got a task doing something, another task doing something else, and another task doing something entirely separate. And they are collaborating, doing collaborative multitasking in order to complete the things all at the same time. You can see how we could use yield in any circumstance to suspend a task temporarily and then bring it back at some point in the future. So for example, if you asked for user input, you could then yield and run your complex mathematical operation. When the user replies, you could yield your mathematical operation and go back to your user input and deal with that. Going back to the example in the lecture a few videos ago. So these yields, all you have to do is put them in the right place, and then you could potentially avoid blocking operations. You could avoid points in time where your Python code is just waiting to do things. Okay. Of course, if you've got a task that doesn't yield, then you have a problem, because that one is just going to clog the CPU. And if you have a task that yields, but it takes a very long time between one yield and another, that task is going to take up a lot of time, and the other task is not going to have enough time. If that's the case, if you have a task that takes a long time to run, while the others take a very small amount of time to run, you could offload the work to a separate thread or to a separate process using, as we've seen already, the ThreadPoolExecutor or the ProcessPoolExecutor. Okay. And actually calling next on a function and sort of going back to a suspended function is cheaper than changing from one thread to another. So Python has been developed, so this is really cheap, really easy to do. So it can be really fast to use these generators instead of threads if that's what you need. Now in the next video, we're going to look at some more of this. And the purpose of the next few videos is to build up your knowledge of how this asynchronous development works up until we arrive at modern Python and how modern Python does asynchronous development. Okay? I'll see you on the next video.
No man is a failure who has friends. And I hope you hang on to the friendships you've made here at Harvard. And among your friends, I hope you find someone you want to share your life with. I spoke about the importance of intuition and how there's no greater voice to follow. That is until you meet the love of your life. And this is what happened when I met and married Kate. And that became the greatest character-defining moment of my life. Love, support.
Hi and welcome back. In this video, I wanted to show you how to yield from another iterator in Python. So let's look at some code. I think that's going to be the easiest way to understand what's going on. From collections, I'm going to import the deck, and then we're going to create a friends deck. And that is going to take in Rolf, Jose, Charlie, Jen, and Anna. And then we're going to have a getFriend function that just does yield from friends. Okay, if we then call sort of C is getFriend, and we do next of C, what we're going to get if we run this file, of course we have to print. That is always helpful. Is Rolf and Jose. So this yield from, you can think of it for now, not forever, we're going to change this soon. You can think of it for now as just getting the next value of another thing that you can get a value from. So what it's getting here is the first element of this deck, and then when you call next again, it's getting the next element of this deck, and it allows you to sort of yield from existing iterators. Okay? Essentially, this has now become a generator that gives you each value of a list or a deck in this case. It's a good way of creating a generator of something instead of doing, X for X in friends, which would be another way of doing this. Let's use this generator now in another function. So what we're going to do is define a greet function that is going to take in a generator, and it's just going to run an infinite loop that is going to try to get the next value of that generator, and it's going to yield hello friend. If it fails to do that because there's a stop iteration, then it's just going to pass and it's going to do nothing. Okay. Now this may not make much sense until we start sort of using this. I'm going to minimize that just so we get a bit more space. What we're going to do is going to get a friends generator, and that's going to be our getFriend. And then we're going to create another generator, which is going to be our greet generator, and that's going to get our friends generator passed into it. Okay, hopefully this makes sense. Our generator here, we can call next on it, and it gives us Rolf. Then we can call next on it, and it gives us Jose, and so forth. We're giving that generator to our greet function, and what that does is it goes over a whole for loop, and it's going to try to get the next value of the generator we passed in. That's our friends generator. That's going to be Rolf the first time, and it's going to yield back to us this string, hello Rolf. If it cannot get the next value because it's run out of values in this deck, then it's going to just do nothing, and we're going to end this loop. Okay, it's going to raise a stop iteration there. Let's have a wee look at how this would go. Again, all that is happening here is we are calling the next of this greet generator, which is going inside this loop and is going to move over to this yield. It's going to yield hello Rolf, and then it's going to suspend. When we press next of G again, it's going to proceed, and it's going to go back into the top of the loop. It's going to get the next value of the friend, and it's going to yield hello Jose. Okay, so the fact that this is a while loop doesn't mean it's going to run continuously, because we've got the yield, so the function is going to suspend every time we call next. Let's run this file again. And you can see now that we get sort of what you'd expect, hello Rolf and hello Jose. What we've got here is some pretty awesome thing, even if it's not so clear yet, because when we call next on this top level function, that is then running this function up to the first element. And then both of these suspend. When we call next again, this one continues, then it asks to continue this one, which then gets the next value, returns it here, and then it yields it back to us. So there's a chain here of calls that are going down our functions. One function is running another, which is running another, but really none of these are running until we call next. So we can use next to start this chain of runtimes, which is pretty awesome. Okay, now let's go over to look at something else. In the next video, we're going to see how the yield statement can be used to receive data. I'll see you there.
You find happiness as you do your duty. You find happiness as you lead a disciplined life before God. You'll have periods of happiness. But God nowhere promises happiness is to be a goal in life.
Hi and welcome back. Something that we are going to look at in this video is pretty mental, and a lot of people in the Python community don't really understand how this works. And that is that you can use the yield statement to receive data as opposed to only give it back. Here's an example. We're going to define a greet function, and this is going to say friend equals yield. Wait, what's going on here? Well, let's have a look. Then we're going to print hello friend. So this looks weird, it looks bizarre, and it looks weird to me too. But what's happening is we're going to say friend is equal to suspend the function. And then we're going to print out the value of friend. And this has been designed this way in Python so that we can suspend the function, but then also receive a value after we resume it. And the value we receive is going into friend, and then we can print that out. Here, we're going to say g equals greet. And the first thing we have to do is run the function up to right before the yield. So we can say g.send none. This is called priming the generator, priming the generator. And what this does is it sort of runs it up to right before the yield, and then we can do g.send Adam, for example. This is what's going into the yield, and the function is then going to assign Adam to friend, and we're going to continue here. Let's run this file. Okay, so we get a couple of things. We get hello Adam, so that's awesome, this works. But of course, we also get stop iteration, because there is a yield here, which means this is a generator, and the generator ends after we print. There's no sort of repetition, there's nothing else to yield, so we get a stop iteration because that's the end of the generator. So this receiving through yield is weird, but it's actually what makes asynchronous Python development possible. Let's look at another example right now. We're going to have our deck. Then we're going to have our friends, which is going to be a deck of Rolf, Jose, and so forth. And then we are going to have a friend upper function. This is going to say, while we have friends in our deck, we're going to say friend equal friends dot pop left dot upper. So it's going to get the leftmost element of friends, it's going to remove it from the deck, and it's going to turn it all to uppercase. This is the way of doing that in Python. Then it's going to say greeting equal yield, and it's going to print greeting friend. Okay. So this is very strange the way this looks. It's going to loop over friends, going to get the first friend and turn it to uppercase, and then it's going to suspend the function until we receive a value here through the yield. And the value we're going to receive is some sort of greeting. And then when we receive that value, it's going to print out greeting and the friend, and then it's going to repeat again, popping the next friend of the list, of the deck, and then waiting again for some data to come through this yield. So the function is going to suspend at this point until we get some more data, and then when we do, that data is going to be assigned to greeting, which is then going to be printed out and so forth. Okay? And then we're also going to have a greet function again. This function is going to prime the generator by sending none to it. So again, it's receiving a generator here, which is going to be this friend's upper here. And it's going to send none to it to prime it and bring it up to the first part of the yield here, just before the yield. And then while true, is going to again take a greeting and yield it and send it over to the generator that was passed in as a parameter. So very weird stuff going on here. Let's finish off the code to see if this makes any more sense. We're going to create a greeter variable, which is going to be greet, and we're going to pass it in a generator, which is going to be our friend upper generator. The first thing we're going to do is we're going to prime the greeter generator. So we're going to do greeter.send none. Again, you know what this does. It just moves the generator up to before the yield. So greeter.send none is going to move the generator up to here, running this primer. So it's going to prime friend upper, and then it's going to stop right before the yield. Then we're going to do greeter.send hello. This string here is going to go into the yield and be assigned to greeting, and then it's going to be sent to friend upper, which is our G. When we do that, that's going to be assigned to greeting. Remember, it was primed earlier on, and then it's going to be printed out using this friend's upper thing. Let's run this. There you have it. Okay, we print out hello Rolf, and that's it. What we've got ourselves here is some pretty amazing thing. None of these functions is running, but they're all suspended, allowing something else to run. For example, we could print hello world multitasking, and then greeter.send how are you, for example. We could run this again. And now you can see that we are multitasking essentially. First, we've got hello Rolf. Then we've got something completely separate from our chain of functions, even though they're running in a loop. And then we've got how are you Jose. And notice how this is taking data from this deck up here. If we have a bunch of this type of things running in a task scheduler, for example, instead of popping from friends, it could be requesting something from the internet, like some pages to scrape. You can see how these could potentially be used to divide up the work by using these yields. And it's pretty messed up, okay? But this is sort of how it works. And this is how Python asynchronous development works on the inside. Now, instead of doing all of this, we can actually do something which is, I don't like it, nobody in the Python community likes it, which is we can do yield from G. Okay? This, which we looked at before, was used to extract values from an iterator, actually can be used for two-way communication as well. It can be used to receive data and forward it to another generator. So here, when we send hello, it comes in here and it gets passed over to G as well. and then it can be used, and then whatever value then gets returned back. So this is another way of writing exactly the same that we had before. Okay, so this send none and sort of repeat constantly yielding things and sending the value can be replaced by yield from G. Okay. So we can easily chain these generators. And when you have generators that receive data, they're really no longer called generators because they're not generating anything. Now they're receiving data and doing something with it. So from now onwards, this type of generator shall be known as a coroutine. Okay, and in Python they're known as coroutines because they take in data and they can be suspended. So that's a coroutine. In the resources section of this lecture, we've got some further reading. It is advanced. So take your time. I don't expect you to be flying through this section by any means. Okay, I expect you to be reading through the extra resources. There's a very long course there on coroutines and concurrency from David Beasley. That's really good. If you're not that keen on sort of knowing everything there is to know about concurrency in Python, feel free to sort of skip through it. But if you want to really understand what's going on behind the scenes, then do read all the further reading and resources that I link you to. So that's it for this video. Hopefully this was interesting, and I'll see you on the next one.
Now what Ken Wilber was saying is that the great spiritual teachers were not just focused on the now, they were focused on the future. Jesus wanted to build a legacy. Buddha preached because Buddha wanted to change the institutions of that time, the way the rich and the poor were. Moses wanted to free his people. Muhammad wanted to conquer and spread Islam to the world. Paramahansa Yogananda came to America to spread the wisdom of India. All of these people had a vision for a future they wanted to create. And that's really important.
Hi and welcome back. In this video we're going to introduce async and await. These two pieces of syntax are fairly new in Python, and they are extremely used nowadays whenever you write any Python code that uses asynchronous development. For example, there are many Python frameworks and sort of libraries that you can use that allow you to run things together, more or less, all in the same thread, but yielding to one another in order to avoid waiting times. And nobody understood yield from. So a new keyword was invented in order to get rid of yield from. And this keyword is called the await keyword. So we're going to rewrite this code. It's going to be a small rewrite in order to use async and await. And you'll see how suddenly it just makes a lot more sense. So let's rewrite this to use the new Python syntax, and you'll see how it makes a lot more sense. We are going to essentially leave this exactly the same, but we now must tell Python that this is not a generator that can somehow accept data. We now have to say this is a coroutine. Okay? So we say at coroutine. And it's red because it doesn't know what it is, so we have to import it. So from types import coroutine. And then it likes it. You must do this in order for us to be able to do the following, which is await G. It doesn't like this because you must do async def there. Now that we've got our async function, this tells Python that it can await coroutines. And when we await a coroutine, that is exactly the same as yield from. Now we can accept data via this send, and it gets passed over to G, which is this generator here, this coroutine, which accepts it through the yield and gets again sent to greeting, and then it prints things out. Notice that when we await, in the same way as when we yield from, this waits for this entire function to finish. So here the while loop, essentially this is waiting for the entire while loop to finish. But it can suspend halfway through. That's the whole point of the yield. So when you send something, this gets passed over to G, which then resumes the function after the yield, and then it will go back over to the start of the yield, and then it suspends. And this function, this line here, still hasn't finished running. When you send some more, then it gets passed over to G, and then it continues this function running. But await G still hasn't finished running until this coroutine has ended. If we print something like starting, and here something like ending, you'll see what I mean. If we press play, you can see that we print starting, but ending is never printed out, because we've not finished running the coroutine. The coroutine has a loop, and it continues running until friends is empty. And we've not gone through all of the friends, we've only gone through 2 of the friends with our 2 greetings. If we wanted to go through all of the friends, we can do that. And just by doing this. And now if we run this again, you can see that we get ending at the end, and then we get our stop iteration, because the coroutine ended. And, when you end the coroutine or a generator, you get a stop iteration to signal that this is the end. So this is really important. The await, just like yield from, they are exactly the same thing, waits for this to finish, but you can suspend the function in the middle. Okay? So a slightly better way of going about this could be that instead of, sending arbitrary greetings there, one of the great things is you can send, for example, hello, but then you can get another thing from the user, and then you can do greeter send greeting. And then you can sort of copy them and paste them again. This is now proper multitasking, because when you run it, now you get the user to type, and as soon as the user types, this then continues running the function above, and it prints out, Jose, howdy Charlie. And then your program ends. We've not gone through all of our friends, so this is how the program ends there. There are more uses, many more uses, of course, for this async and await syntax and for concurrent programming in Python as a whole. So all you've seen so far is some sort of abstract examples that I've just shown you there, but we need to look at a way to use these functions in the real world. Okay? In the next video, I'm going to suggest that you watch a few talks, and those talks, again, will walk you through what async and await mean and how you do concurrency in Python, and they will also include some real-world examples. And then afterwards, we're working to add some more content on the course about some real-world examples of using async and await. So if that's not yet in the course, just check back later on and we will be adding it in. Hopefully, though, now you understand how async and await work, and that's by using these generators. With that said, I'll see you in the next video.
Well, the one thing I would definitely say is there's no do or die in this world. Nothing is important enough for you to take so much pressure that it defines your life. You have to be like water. Learn to be like water. Adaptable, fit into any vessel, have a sense of calm, have a sense of patience. But ambition is extremely important. And I don't just say this to girls, I say this to boys and girls. Just everyone who wants to be able to have a purpose in life, have an ambition, have the guts to find your glory. It's extremely important to have guts, to have conviction, to be able to say that, this is what I want and I want to achieve it.
Hi and welcome back. In this video, I wanted to encourage you to watch the talks. I've linked them as resources to this lecture. Now that we've explained a lot of how concurrency, doing multiple things at the same time, works behind the scenes, I think it's time for someone to walk you through a couple examples. And the reason I've picked these guys and these talks instead of just doing it myself is because these two guys actually developed asynchronous development in Python. They are Python, the creators of the Python language, or they help create the Python language. So they're really poised to guide you perfectly through these examples without, misguiding or doing anything incorrectly. That doesn't mean they're perfect by any means, But it is a really complicated topic when you start getting into the depths of how everything works behind the scenes. So I think we've done a pretty good job of explaining what's going on. These guys are going to take you that one step further. And that's going to be the case with any course you take or anything you do. There's always going to be more research, more things to learn. And by going to conferences and listening to talks, like these ones that I'll link you now, is a great way to do that. However, of course, the purpose of this course is for you to learn the most you can. And as such, come back to me with any questions you have after watching the talks, and I'll be more than happy to help you out and answer any questions. Again, watching conference talks and going to conferences is a great way to learn more about obscure and complicated topics like asynchronous programming. And of course, working with it, doing some programming with it, is a fantastic way as well. So watch the talks, and then come back to me with any questions. I'll see you there.
I found that it suited my aptitudes to take that money and buy assets and hold those assets. Having a historical bent allowed me to see the market through the prism of history. And so when you see these cycles and you understand human psychology and fear and greed, the history gives you a great perspective. And so if you own the assets and you don't go into debt, it really becomes a function of time before you become fashionable again. And we made a huge discovery in Bolivia, and that's where the fortune originated.
Hi and welcome back. I hope you've watched the talks from the last lecture, and in this one we're going to be turning our scraper that we created earlier on into an asynchronous scraper. Just to use the stuff that we've learned, and also a couple of things that were mentioned briefly in the talks that we're going to explain as well. So when we looked at scraping websites before, we sort of got up to 50 pages here, one after another, from our books.toscrape.com site, but it could be a bit slow because of all these pages. And if you remember, when we ran the menu, which I'm going to do just now, we then sort of had a period where nothing seemed to happen. And this was when the pages were all loading. And eventually, something appears once all the pages have loaded and we've extracted all of the books into our sort of master books list. I'm just going to exit this menu and collapse that. So if we could do this asynchronously, we could increase the speed massively. And the reason for that is as follows. What's happening here is that the first thing we're doing is we are sort of, creating a new string, fairly straightforward. Then we're requesting it and getting the page content. And then we're sort of logging something, creating our books page and sort of extending that. And the main improvement from using asynchronous requests, which we're going to look at soon, is in this line here, line 22. The reason for that is because there are a few things happening in the background when we do this. This line starts a request to the server, sends some data to the server telling them, hey, I want to, start a connection to you. And then it has to wait for the server to respond. Once that connection is set up, it has to ask the server for the URL that contains the page content, and it has to wait for the data to come back. It has to download the entire page content and wait for all that data to come through. So as you can see, there were a couple of times there where we're just waiting for the server to give us something, to tell us that the connection has been set up, or to tell us that the data is now ready, and of course for us to download the data. And from what we've looked at in asynchronous programming, wait means potential improvements from using concurrency. In Python, we cannot run two things at once unless we use the multiprocessing module, but we could potentially send the server, hey, give me this, hey, give me this, hey, give me this, and then just wait for all three at the same time. The server will presumably be able to respond to these requests more or less quickly, and then we won't be waiting too long. We'll only be waiting for the server to respond to all three more or less simultaneously. Okay. just as we did with our simple generator task scheduler, where we had our 3 countdowns and we sort of started one and then started the other and then started the other, and then we used next to go over each one, we're going to be doing something like that. We're going to be having a task scheduler, but we're going to use the Python Async IO library in order to loop through the various tasks that we'll be creating, and each task is going to be responsible of fetching one of these URLs. So we're going to have a task per URL, and we're just going to start them all at the same time using yields, and we're going to sort of wait and resume and suspend them as data comes back. Okay. We're also going to be using a new library called AO HTTP, and we've previously used the requests library, like we've done here. But the requests library does not allow us to make requests asynchronously. It just doesn't have that juicy yield statement inside. So AO HTTP does have them, and it's all set up to be used with Async IO. So we're going to be using that throughout this next few videos in order to turn this into an asynchronous web scraper. So also as a reminder, the Async IO library is built in. AO HTTP is a third-party library. So just a minor distinction. We're going to be looking through that in this section. So let's move on to the next video, and we'll start with making our first request with AO HTTP. I'll see you there.
But I don't respect a lot of people. Because how am I going to respect you, not you personally, but anybody, if you're not fucking grinding every day? And I don't mean working out, getting to the gym. Really going out there and grinding. So if you don't know how I'm living my life, how am I going to respect you? So you have to be a hard worker, period, dot. You got to work your fucking ass off. That's where I gain respect for you. So if you're working hard every day, now you have an opinion in my eyes. But if you're just a guy who talks shit and you live this fucking life of talking shit, come on, dude. I understand one thing. You're just talking shit. But if I see you every fucking day of your life trying to be better, every day, going through all the wickets to be better, you got my attention. I respect you now.
Hi and welcome back. Let's make our first request with AO HTTP. Here in this project, I'm just going to create a new file just for testing AO HTTP, and it's going to be called async request.py. By the way, the code for this is linked in each lecture and is available, maybe in a slightly different setup, but nonetheless, there's going to be a samples folder for you to look at these codes that we're going to write over these lectures. And then, of course, at the end as well, when we turn the full thing into an asynchronous scraper, the full code is available as well. So in order to make our first web request, the first thing we need to do is, of course, to install AO HTTP. Now, soon we're going to look at how to handle dependencies in Python projects a bit better. But for now, we're going to stick with installing things directly in PyCharm by doing, going over to our project interpreter, and there with the plus installing AO HTTP. The current version that I'm using is 3.0.5. This may be different when you're using it, but don't worry. If there are any breaking changes, we will re-record with a new version soon. So if you install this and you notice that things don't work quite the way you expect, just say in the course Q&A, and we will re-record as soon as possible. Okay, just install this package, and this is all we need to install. So when that's installed, you can close this window, and we can begin using it. So that's it, done. We can press OK, and now we can import AO HTTP. So let's first start with fetching a single page. First thing we need to do is create the coroutine. Remember, this is like a generator that can suspend and resume their execution at any time by using a wait. So we're going to do async def fetch page, and what we're going to pass to this function is the URL that we want to fetch. Now the next thing we do is we must tell AO HTTP to create a client session. A client session just essentially creates a bunch of connections and puts them in a pool, pretty much like a thread pool, except it's a connection pool, so that we can reuse them without having to create new connections each time. So what we're going to do is a bit of a new bit of syntax. Async with IO_HTTP.client session as session. All that's happening here is we are doing a normal context manager. We're creating this new client session, which is a connection pool and also a cookie storage. We're going to talk more about that soon. We're calling it session, but because it's async, what happens in an async in an async context manager is that it can have a yield in the enter or in the exit methods or in both. So essentially, it's just a way of potentially suspending the execution of the context manager when it starts or suspending it when it ends and resuming it. Just adds like a new point where it can suspend and resume, just in case you want to do something a bit heavy duty inside the context manager. It allows you to suspend and resume at the start or at the end of the context manager. That's the only difference with the normal context manager and the async context manager. For more information about this, instead of enter and exit, the new methods are aEnter and aExit. Okay? We're not going to get into too much depth about creating your own asynchronous context managers. Just know that if you want to create an asynchronous context manager where you can do an await or a yield inside it, you have to use aEnter and aExit instead of enter and exit. Nonetheless, just a bit of an aside there. Then we're going to do async with session.get, and we're going to get the URL as response. And then we're going to return the response status code. This can be our first task. This is a coroutine that, first of all, creates a session. Then it sort of gets the URL we passed in. It asks the server for the contents, calls it response, and then returns the response status. But of course, before returning the response status, it can potentially be suspended here or here, when it starts or when it ends. So when we can, for example, get the URL or send the request to the server and then suspend while we wait for data to come back. When the data comes back, we'll be at the at the end of the enter section of the generator, and we can continue execution, and then we can get this status. And this is not asynchronous, this is just a normal return. So then the function would end there. Remember, the only purpose of async IO and these asynchronous functions is to potentially suspend execution at any point and resume it after. Placing these things in the correct places means that we can suspend execution when we're waiting, and we can resume execution once we want to stop waiting. Okay? Now, we must have a task scheduler that will do the, dot send or the next. Remember, this is just yield from. Inside here, there are awaits, which are yield froms. So we need something that is going to do this send or this next. And now, as of Python 3.4, I believe, we have that, which is the async IO library. If you've watched the talks, which I hope you did, you will have seen async IO mentioned a couple of times. The async IO library comes built in Python, and it's very small. It's not that small, but it's fairly small, the things we have to know. And it allows us to schedule and manage these coroutines, these tasks. It's really straightforward to use, at least the way we're going to do it right now. There's a bit more to use than what we'll cover, but in order to use it in some ways, it's fairly straightforward. All we do is we get an event loop, and then we do loop run until complete fetch page of, for example, google.com. When you call fetch page, you don't get the response status. We know this already from what we've looked at earlier. When you call fetch page, what you get is a coroutine object. So this isn't actually giving you the response, even though we're calling the function. All this is doing is creating the coroutine in the background that you can then send or next to. When you do that, it sort of goes through each resume and response. So what this run until complete is doing is it's using this event loop in order to continually resume this function until it's completed. Okay. So we can run this. We can right-click the async request and run it. And of course, we didn't really print anything, but we can print response status here, and you'll see that something does come back. Yeah, 200, which means it's all okay. As you can see, this did run. So this is the simplest way that we can get an event loop and run a task. And a task is just an async function that has been defined. Okay, all we need is to get the event loop and run it until it's complete. If you wanted to make more asynchronous requests, we're going to do that just now as well. What we're going to do first of all is import time, so we can start measuring how long this takes. Then, before we do any of the session or anything like that, we're going to do page start is time.time. And right before we return, we're going to print that the page took time.time minus page start. I call it state. No, should be start. There. Okay, if we run this again, you'll see that it says page took 0.17 seconds, so it was pretty quick. The program as a whole took a bit longer, but that's because it involves creating the event loop and starting new tasks, scheduling them, and so forth. But the page request itself only took 0.17 seconds. If you ran this using the requests library like we did earlier on, it would take more or less the same amount of time. Okay, there would be no difference, just because all we're doing here is running a single request. If you want to run multiple requests, though, we can do that very easily. We'll say something like tasks is, and now we're going to do a list comprehension where we're going to fetch page of google.com for I in range 50, let's say. Okay, so now we've got 50 coroutine objects that need to be ran. So how we're going to do that? Well, we're going to say loop run all these tasks until they have been completed. But we can only pass a single task to the run until complete function. So async IO comes with a pretty handy function that allows us to, collect a bunch of tasks together and run them as a single task, so that it's a bit easier to do this. And all that is async IO.gather. And we're going to pass it all the tasks as arguments. So it would be tasks 0, tasks 1, tasks 2, tasks 3, and so on until 50. Or, as you already know, we can use argument unpacking to do star tasks. Okay. Now, as part of this, I'm also going to time this. So I'm going to say start is time.time, and end is going to be all took time.time minus start. Notice how I'm only measuring the loop run until complete. I'm not measuring the creation of the tasks, because this is pretty much instant. No requests are actually happening in this line. Only the coroutines have been created. Then when we start running them, this does the .send to the first task and runs it up until the async IO. Then that suspends, and this moves on to the second one and moves it up till there. Then this suspends and moves on to the third one. So first of all 50 tasks will end up here. Then one by one they will be moved here. And then one by one they will return. But of course, they may take different amounts of time. So one request to google.com may take 0.5 seconds if it's a very slow one. Another one may take 0.1 seconds. So as soon as you start doing this and you only resume execution when you are ready to do so, you'll see that these tasks are not necessarily all going to finish in the same order. Okay, so let's press play. And as you can see, that was extremely quickly. We've got some tasks that took 0.32 seconds. And as they finish more or less in order, we can see that at the bottom, some of them took 0.46 seconds. And in total, it took 0.48 seconds. Not the addition of all of these things, but rather the longest one plus a couple of milliseconds just to set up the event loop and, do the scheduling of the tasks and so forth. So this is amazing, because now instead of having to wait for each page to finish before we get the next one, we can essentially just send the 50 requests out to Google and just wait until they come back. Now, of course, that's going to depend on whether Google can deal with 50 requests at the same time. Google is a massive company, has a lot of servers, and they can handle 50 requests at the same time. Other websites won't be able to handle 50 requests at the same time, and if you do that, you may actually break them. You may actually break the site, or they may say, no, you cannot do 50 requests at a time. I'm going to be very slow in responding to you in order to prevent you from breaking their server. So that's a couple of things you need to be careful about. But as you can see with Google, this is all you need in order to get 50 pages asynchronously. So again, what we've done is we've created our task, and using AO-HTTP, which supports these async with statements, we have created our session and then used that, which gives us a connection pool to get each URL that we passed in. And at the end, we've returned the response status code. That's just to, get something back from there. And then in order to run them, we've got an event loop from the Async IO framework. We've created all our tasks, which are just these functions. And then we've run them all until complete by using Async IO gather. And gather collects all our tasks and allows them to run as one in this run until complete. Otherwise, you would have to do run until complete once for each task, which would be a bit more tedious. So Async IO gather, pretty good for that. Now, that's it for this video. I just wanted to show you how to go about making these asynchronous requests. Feel free to compare this with your synchronous code. If you open app.py, by the way, you can see this is a synchronous code. So if you replace this for google.com and put a couple of timing functions in here, you'll see how long that takes. It's about 10 seconds, whereas this was about 0.5 seconds. So now what we're going to do is we're going to just make this a bit more efficient, get a couple of functions in here to deal with getting multiple pages more efficiently, and then we'll move on to turning our scraper into an asynchronous scraper. I'll see you on the next video.
I just love growing. Like I said, I think growing is a very important thing. And when I was very young, I started working when I was 17 years old. And I remember my mother telling me this really young, that women should be financially independent. It doesn't matter who your father is, doesn't matter who your husband is going to be, it doesn't matter who your brother is, it doesn't matter who the man in your life is. You need to be responsible for your finances and be financially independent.
Hi and welcome back. In this video, we're going to be making it a bit more efficient to get multiple pages. Here in this function, you can see that we've had to create a client session. And each session, as I said earlier, contains a pool of connections so that not all connections have to be created each time. And also contains a cookie storage so that any cookies that websites send us can be shared across requests made with the same session. If you're not sure what cookies are, I've attached a resource link to this lecture just with a brief explanation on what they are. So we then use the session, which uses a connection from that pool that was just created in order to get the URL and get the content and so forth. It sends a request to the server and then awaits the data to come back. The function can suspend at that point until the data comes back. But of course, we said that we've created a connection pool here in the client session so that we don't have to recreate the connection every time. But we've not really done that, because each time we do this, we create a new connection pool. So instead of a single connection, we're creating a whole bunch of connections each time we want to fetch a page. And then we're only using one of them. So this is not great. Instead, what we should do is create the session and use it for all the URLs we want to request, instead of creating a session for each time we want to request a URL. So the way we're going to do this is we're going to split this out into another thing that is going to allow us to create multiple tasks. So async def, get multiple pages, and to this thing we're going to pass the loop and also the URLs we want to get. Notice that this is an unpacked argument there, so we can pass in many different arguments, one for each URL that we want to get. Then we're going to say tasks is an empty list, async with AOHTTP.client session. And to the client session, we can actually pass in the loop that we want to use, which is the one we create down here. And the parameter is going to be this loop. The reason to do that is just so it doesn't create a new loop. Now, when you do async.io.getEvent loop, no matter where you do that in your program, it's always going to give you the same loop. But in case you forget to do that, passing the loop in here can be quite handy, just so not a new one is created that maybe runs independently or doesn't run until complete. So this is just a safeguard to make sure that you use the loop that you've defined earlier. So with AOHTTP client session as session, we're then going to populate our tasks list and wait for them. So for each URL that we've got here, we're going to say tasks.append fetch page of this session. The URL. Like so. Now, when we do this, what we do is we call this fetch page function. That creates a coroutine, and that gets then put into our tasks list. At the end of the loop, but inside this statement, this context manager, we're then going to wait for them. Okay? So grouped tasks is going to be async.io.gather. And this is going to be our tasks. Again, all this is doing is gathering all the tasks that we've put in our list and is treating them as a single task so that we can then execute it in a loop, like loop run until complete. Except instead of running them using this loop, we're going to await them. So return await grouped tasks. This, all it's going to do, as you know, is, yield from. So it's going to allow us to suspend the execution here and wait until something happens here and then resume the function and possibly repeat all of that until this returns. And this will return when all of the tasks are finished. Okay? So when we do this, now we can run until complete this get multiple pages. Let's finish off this code before we review it and make sure that it all makes sense. This fetch page is still creating its own session here. We don't want to do that. So what we're going to do is delete that entirely and then make sure that we pass in the session. Smession. Make sure that we pass in the session correctly spelled there. And then pass it in here as well. Just so that has access to the session we've created. Okay. Now our tasks are no longer going to be fetch page. They're just going to be the strings. And we shall not call them tasks. We're going to call them URLs. So now we have 50 times google.com inside our list. And what we can do is run until complete our get multiple pages with the loop and the URLs. Notice how URLs is a star URLs. And so we must also pass in the arguments individually by unpacking them. If you prefer, you could just pass in a list. That would be fine as well. And then all you'd have to do is delete them too. It's up to you how you want to do that. All right. So what we've got now, let's review that, is 50 strings of google.com. Then we pass them all to this get multiple pages function. And we also pass in the loop that is running through as a task scheduler. So they go in there. The loop is used in the client session just so it doesn't create a new loop in case we forget to pass it in or we forget to create one. It will say, hey, you didn't pass me anything. Something's wrong. So this is a safeguard. And the URLs, we are then going to iterate over them and append the coroutine that they create into our tasks list. Remember, we could suspend the function execution before or during this creation of the session, But inside it, once we go in it, it doesn't suspend at any point. All it does, it iterates over all the URLs and creates all the coroutines synchronously one after another. There's no suspension anywhere inside here. So we create all the coroutines, and then we're going to gather them as one. What this does is it essentially awaits each task and only returns when they're all complete. We then await that. So if we want to suspend, we can suspend in between each task, or we can suspend at the start before we start any task, or we can suspend at the end once all the tasks are finished. That means that these tasks that we group here are all running individually in this event loop. So that is what this gather does. And then we return the awaiting of that. So this function only returns when this has finished running, but it can suspend on the way. So when it has finished running, that returns, and that is the end, and that function has run until it has been completed. So that's why we do run until complete. Run until complete is going to run until this return actually executes. And that's only going to execute when this has been fully awaited and this has completed itself. And once that happens, we can print out that all of them took the amount of time they took. It seems slightly more complex, but there is a key performance improvement, which is that you're not creating a session for each of the pages that you want to fetch. And of course, as long as you do create your event loop first, this thing here is not necessary. You could not pass it in if you want. It's totally up to you. Either of them will work. So you can run this, and as you'll see, you still get the same thing. Yeah. Notice how they seem to take slightly longer now. This could be due to any number of reasons. Somebody else using the internet in the house, or Google being more hammered down by somebody making requests, or anything else. If you do want to pass the loop in there, this is fine as well, and this is what we did earlier, and it'll work in the same way. It seems like this was now faster, possibly because it didn't have to go and get the loop each time. So this is possibly a performance improvement as well. Anyway, that's it for this video. I just wanted to show you how to make this a bit more generic in order for you to then be able to use this in our book scraping program. So if you want to go ahead and try that out, try to turn our book scraper into something that uses these two functions and an event loop to get all the pages instead of getting them synchronously, I'm pretty sure you can do that now. All you have to do is import a couple of libraries that we've already installed, copy these functions, and then instead of going through each URL one at a time, get them all at the same time first, and then you'll be able to use their contents. Again, it may be slightly complicated, it may take some time and some investigation. Once you're done, or if you want to see how we do it, come back and we will implement that together. Okay, I'll see you in the next video.
I believe in the power of wandering. All of my best decisions in business and in life have been made with heart, intuition, guts, not analysis. When you can make a decision with analysis, you should do so. But it turns out in life that your most important decisions are always made with instinct, intuition, taste, heart.
Hi and welcome back. Just a quick aside to warn you of something that can happen in these asynchronous programs. Because we're running until complete, and we're gathering all the tasks here, potentially if one task takes a really long time, or maybe it takes a few minutes or a few hours for the server to respond, we want to say, if it takes more than 30 seconds, I just want to terminate this and treat it as an error. Sometimes the servers won't send you an error, they just won't send you anything, and you'll be waiting for content for a long time. This run until complete means that your program won't actually finish until all of the tasks have given you something. And so it can be a bit dangerous if you don't have anything to say, time out after X number of seconds. AO-HTTP in the latest version comes with something called the async timeout, which you can import, async timeout, that you can use as a timeout in an asynchronous environment. So you can just say async with async timeout, dot timeout, maybe 10 seconds. 10 seconds is a pretty reasonable number, I think. So now if this session get takes longer than 10 seconds, it's going to be cancelled and exception is going to be raised. And as I said, that can be quite handy for when something does take a long time. For Google, this is not going to be a problem, but maybe for a book scraping business, it could be a bit of an issue. So that's it for this video. I just wanted to share with you this async timeout as something that exists and that you can use. I'll see you in the next one.
I have the most respect I can possibly muster up for all of you in this room. I know what it takes to be a combat soldier, and I used to look for courage. I thought courage was a man who won the Medal of Honor. It is. But courage is a man who's willing to put those boots on every single day of his life to go out there and fight for this country where nobody even knows what the hell they're doing or where the hell they're at. You do it for the man beside you. Thank you.
Hi and welcome back. I'm really excited to guide you through turning our scraper into an async scraper. We're gonna see a few things that may be a little bit surprising throughout this video, but generally, you're gonna see massive performance improvements from doing this. We're gonna start with re-implementing our functions in order to make them async. So, we're gonna have our fetch page and our get multiple pages in here. I'm going to go into the async request and just copy them because they're going to be exactly the same. That's the reason why we've covered these two functions, is in order to allow you to reuse them throughout any project. Of course, we've got a few imports missing, so let's make sure to import them. We no longer need requests, so we can get rid of that. We can import async IO, IO-HTTP, async timeout, and time. Time is just for the timing. We can remove it later on if we want. Notice how we've got this requests page here. So actually, we do have this separate requests in there just to get the number of pages that we're going to request. Remember, we started at 1 and we got up till page count. So actually, I revert what I said earlier. We still need import requests. And that's totally fine. You can have synchronous code surrounded or joined by asynchronous code side by side. That's totally fine. I just forgot that we were doing this to get the number of pages. This is okay. You could potentially turn this into an asynchronous request, but because it's a single request that we're doing first in order to get the count, it doesn't make sense to treat this asynchronously. After all, it's just one request. You have to wait for it to finish before you can get the data. So there's no benefit from running one thing simultaneously as itself. So this is going to still be synchronous. That's okay. And then we're going to have our two functions here in order to fetch the page and get multiple pages. And then we can call them down in our loop. Notice how our loop is iterating over the page count, and then it's going to get each URL using requests. We no longer want to do this. We no longer want to iterate over the range and get each page. Now what we want to do is get all the URLs and pass them in to our get multiple pages function. So what to do is to copy this and put it in a list comprehension. Like so. And you can call them URLs, for example. Again, all we're doing here, and by the way, I'm going to close the sidebar just for your benefit there so we have a bit more room. What we're doing here is just putting this inside the list comprehension between the range 1 and the count. Exactly the same as we were doing here, but except we're no longer iterating over it, we're just creating the URLs. Then we're going to start a timer just to check out how long it takes. I want to do pages equal loop dot run until complete. get multiple pages with the loop that we'll create and all our URLs. We're going to create the loop at the top. That's just sort of the normal thing to do, create the loop at the top. We're going to say loop is asyncio.getEventLoop. That's all. Now we can use this loop to run things until they're complete. Okay. Then at the end, we can print that it took some amount of time. Print total page requests took time.time minus start. Okay. Now, these pages, what is the value of them? Because the loop has ran this thing here until it completed. This thing here returned an await of the grouped tasks. So what is the result? Well, fortunately, this works exactly as you would hope. These group tasks, which is this gather thing, then gets returned as individual elements in a list of the results of all the tasks that were ran. Notice how each task returns the response.status. So in this return group task, what we're going to get is a list of statuses for each page that returned. Okay, they could be in order, they could not be in order depending on how long each one took. Okay, so instead of returning the response status, we're going to return the response text. That's just the HTML contents of the page. But because this can take a while to download, IO_HTTP actually lets us await it so that we can suspend before we start downloading and resume once the download has completed. So really great stuff there. Now that we are awaiting the response text, these pages here are actually going to be a list of all the pages that we've downloaded using our tasks. So what we can do then is say for-page content in pages. And here is where we are going to create our all books page and extend our books list. So we're going to copy that there. And that's it. This is all we need in order to make this code asynchronous. Okay, so let's cut that off and run this and see what happens. Bringing back this sidebar here. We're going to right-click the menu and run it. And you can see what's happening here. It is not so fast. It is in fact pretty slow. What's going on? Google was so much faster. And you can see that they didn't all run at the same time. You know, there's one here that took 0.23 seconds, and then there's one here that says took 8 seconds. And you know, the first time I saw this when I was preparing the notes for this course, it actually took me a wee while to realize what was happening. I thought, why is one of them taking 0.2 seconds and the other one's taking 8 seconds? I thought, are we maybe running these not asynchronously? Are we doing something wrong? But as we've seen, we just literally copied what we did earlier that did work for Google. So this is the reason why we copy and pasted this code, just to make sure that it was all correct. Sometimes it can be a bit difficult to debug and find out the issue with asynchronous code, just because, you know, you're suspending, you're resuming many times throughout various functions, especially if you have something like 50 functions that we do here, all suspending and resuming. It can be difficult to debug if you use PyCharm's debugger. So it's easier to start simple, start small, like we did earlier on in our async request file, and then try it out with a larger thing. And the problem here is just that the books.toScrape server doesn't allow us to do all these requests at the same time. It just does them one by one. And it returns one by one. And because we've sent him 50 at the same time, hey, the first one's going to be quick. But then it's doing the first one. And when that's done, it does the second one. And so forth. So by the time it gets to the end, what you're essentially looking at is the sum of all the requests you've done. Each one takes around 0.23 seconds. So the first one takes 0.23, the second one takes 0.4, 0.6, close to 0.8, so forth. So it just gets added each time. You can see that it's returning them one by one. So this is a problem with the thing we're scraping, not with our code, which is a good thing. If you were to scrape a page that isn't a test page, something like Craigslist or Gumtree or John Lewis or some big reseller like that, but some big department store, you'll see that these will all come back at the same time. Okay, and if we change this to google.com again, just to go back to what we know, and we run this again, you can see that, it's instant. They are all running at the same time. It's just that the other one, the other page doesn't let us get them all at the same time. So we're going to stop this. Remember to stop your programs when you're running in PyCharm. It can be something you forget. So if we were able to run our books.toscript.com asynchronously, you'd expect it to take around 0.3 seconds, 0.4 seconds in total. But because it doesn't, it takes much longer. Okay, that's just a limitation of what we're scraping, not of our code. I'm assuming that when you're building your own scraping projects, you're not going to be using this test scraper, this test website. You're going to be using a proper website, and that's almost definitely going to work just fine. I've tried it with a bunch of other websites, and they all seem to work okay. So that's it for this video. This is all you need to turn this into an asynchronous scraper. Remember, the majority of our code, creating the all books page, and going through and parsing and stuff like that, that's instant. There's no waiting involved here. That's just Python doing work. There's no waiting for somebody else to give us things. The only waits are happening when we make the web requests, and that's what we're running asynchronously. The rest of our code is running synchronously because it doesn't need to run asynchronously. It's really quick. There's really no waiting time. The performance here is not an issue. So that's it for this video again. Thanks for watching, and I'll see you on the next one.
And he say, Cristiano, we have money, we have everything, we have fame. And he say, I have millions, billions, but the most important thing, it's the family. Keep your family healthy, good, and take care of your family, because this is the most important thing in the world. Apart of that, of course, you have your life, your private life, you have your girlfriend, but in the beginning, your family, it's always with you, for the good moments and for the bad moments.
Hi and welcome back. I just wanted to give you a little bit of information about macOS, if you're using macOS, and HTTPS URLs. As you can see here, we've requested http.google.com. In our app, we requested http.books.toscript.com. And we never made an HTTPS request. For example, something like this one. This is John Lewis. It's a pretty big shop in the UK, but its website has HTTPS. If you have just now installed Python, maybe at the start of the course or recently, and you're using Python 3.6 or 3.7, it's possible that when you run this program, it will fail. Linked to this lecture, I've got a bit of code that you can run to see if your Python is set up correctly. And if running this code fails, that means that you've got a missing piece of configuration in your Python code. This is fine. If you are using macOS 10, your Python doesn't come with a library that it needs in order to essentially verify that these domains are actually secure. So OS X, macOS 10, provides deprecated or old versions of an important library for verification. And this library is called OpenSSL. And Python 3.6 and 3.7 got tired of using these deprecated old versions. So now Python 3.6 and 3.7 and probably newer versions as well are shipping with their own version of this library. Because it's their own version, it means that all the certificates, and keys and things like that your computer trusts by default, your computer says, johnlewis.com is, this is secure because this certificate was created by this organization that we trust. Python doesn't trust those organizations by default because it's a completely different library than the one that comes in your computer. So if you want to make Python usable with HTTPS, what you have to do is you have to install something that is inside your Python folder. So I'm going to bring it up. What you want to look at is you want to find your Python folder in your applications, and notice how it's Python 3.6, and then I've got Python 3.7 here, which is a new version. There is a thing here called install certificates.command. All you have to do is double click that. And when you do that, this will work. Okay, so all you have to do is double click that. That is going to install the certificates that you need in order to trust these secure domains. Again, the code linked in this lecture has some more information on why this is happening and you know how you can fix it. So that's it for this video. Just wanted to tell you about this because it's a frequent problem when you start making these requests, and it can be a big pain in the ass to solve, especially if you don't know what you're looking for. That's it for this video. I'll see you on the next one.